Okay, so today we'll probably get through certainly the exceptions to the octet rule, drawing them. Formal charge is something that you must use when drawing structures. And they will definitely ask questions related to formal charge. I've even seen specifically like a chart written out that you need to draw on a free response question. So formal charge won't go away, but you won't use it so often as we get towards the end of the year. You'll use it a lot right now, but they will definitely question you again for it. And then bond energy and bond length is similar to kind of honors chemistry style thinking about terms of how strong a bond is, depending on how many bonds you have. And then I don't think that we'll get to resonance structures today, but you've done those before. All right. So exceptions to the octet rule. Sometimes we don't get octets. So we can have an incomplete octet, like this example of boron. And when we go to fill it, we want 8, but it only will take 6. So the reason why this is if you look at the periodic table, boron only has 5 protons. So its ability to attract 8 electrons or surround itself with 8 electrons is unlikely. So it's not going to be able to hold on to more than just the 6 electrons surrounding it. This also happens with beryllium. I don't think it's in your notes, but beryllium only needs 4. Jot that down. So beryllium will only ever have 2 bonds. So boron needs 6. Beryllium needs 4. Those are the 2 that will get an incomplete octet. Then there's a few others that we'll look at that are expanded octets. So an expanded octet occurs in periods 3 through 7. They can bond with other atoms in such a way that they end up with more than 8 electrons in their octets. They're able to do this because they have d orbitals in their outer shells that can accept electrons. So when we typically look at the periodic table for electron configuration, we have ns2 and np6 as our outer shell, right? But within the ns2, np6, there's always a d sublevel, well, starting at period 4, the 3d sublevel enters. So I could potentially not just fill electrons into the s and the p orbitals, but I could fill them into the d orbitals if I wanted to. So this happens with a few of the atoms. And they all kind of do it similarly. And if you draw your structures the way that I taught you to draw them, you will automatically see this occurring. So expanded octet, this is PCl5. So what happens is phosphorus will take some of the electrons and put them into the 3D sublevel. So it says 3D and 3P have similar energies. Thank you. And so it will just automatically take the extra electrons and put them in there. The 3D sublevel is not full in this. In fact, you can just add them in there. And there's still plenty of room for extra electrons if that happened. So if you were to draw this structure, PCl5, you would end up with this by default because you'd have to attach 5 terminal atoms. You can't just stop and attach 4 and say, well, I don't know what to do with my other Cl. Maybe I should attach it down here. You can't just stick it on to another terminal atom. You know that this is central. So you would automatically make your octet expanded. Do you agree? And then once you checked all your electrons, they would add up and subtract to give you that there's nothing on the central atom. So this happens with SF6 also. Same idea, the 3D sublevel is not full. So the extra electrons go into the D sublevel because it has similar energy to the P sublevel. So it just takes these extra electrons and puts them in there. So how many electrons were put into the D sublevel? So go ahead and look at that. So you would need to look at sulfur on the periodic table. How many electrons are there total surrounding sulfur? Count them. 2, 4, 6, 8, 10, 12. How many are in the outer shells? NS2, NP6. This is the general electron configuration for a valence shell, right? How many does the valence shell always take? 8. So if this has 8 valence electrons that it would accept, how many went into the D sublevel? There's 12. And then there's 8. So that would be 4. We're struggling here? When electrons, look, when you have an s orbital and you have your p's right? They start filling. Once they're filled, plus you just saw that I filled those incorrectly. I'm supposed to go one up, and then down, down, down. So those are filled. These are sharing electrons. So once they've shared, now you have extra electrons. There's 2, 4, 6, 8, 10, 12 total electrons in this structure. So 4 of them, since 8 were used here, and there's 12 total, 4 went to the D sublevel. Okay? Sulfur does have a D sublevel, even though it's in the 3rd energy level. You don't see D, but if you go to the 4th energy level, you would say 3D. There is a 3D sublevel that exists in the 3rd energy level. It's just not being occupied for sulfur. It's empty. But it exists there. It's just an empty orbital, so they could possibly go in there. All right. Yep. Did you get it? All right, xenon will do the same thing. So xenon expands its octet. Some of the electrons are promoted, in this case, to the 5D sublevel. 5p and 5d have similar energies, so they go there. So this structure, you may have thought, well, I don't know that I would come up with this one. Well, I want you to try this. Just here's obviously the structure. I want you to try the math that we learned last week, so get your little note card, and draw yourself this structure so that you see that you would end up with the expanded octet, and then we'll look at it. So let's see. Letter A. M, you want to try that? So least amount of potential energy associated with its bonds. So look, high potential energy, low potential energy. Things that are closer together have lower potential energy. So it is number 1, lowest potential energy. If you look back at the slide right before this, we said CCl had the lowest potential energy because its atoms were closest together. So lowest potential energy as it has the shortest bond length. Part B, which bond has the lowest bond energy? All right, lowest bond energy in your mind means which of these is going to be easiest to break? What is it?
I said it was the second one.
Yep. It's exactly what it says. So it's the second choice, lowest bond energy as it has the longest bond length, so therefore it's easier to break. It would require less energy to break a bond that has long bonds. As in this case, potential energy would be higher, right? All right, bond energy and bond length. We're just going to go through these, I think, next 4 slides and then stop before we get to resonance structures. As the number of bonds between 2 atoms increases, the bond length decreases and the bond energy increases. Lots of words here. So basically this is what's happening. Single bonds are longer than double bonds, are longer than triple bonds. We know that. And what we'll look at when we start looking at geometries is that in a triple bond, we have S orbitals bonding and P orbitals. And P orbitals are dumbbell, and they kind of are up here. And so when they bond, they just kind of grab the molecule and squeeze it together like a spring. Versus S are just head to head. So a single bond's like this, kind of moving around, and then you add a P bond and it starts pulling the molecule tighter, and then you add another P bond and it's pulling it tighter. That's why your triples get so tight and bond short. So this is much harder to break than this. So bond energy increases as your bond length decreases and the number of bonds increases. Lots of words, but I think you get it. So this is showing you the bond type. So we have single, double, and triple bonds. High bond energy for a triple, and look, the bond length is decreased. Which of these has the lowest potential energy?
Triple.
The triple has the lowest potential energy because you have closer atoms. All right, bond order. I think this is the last one that we'll do, and I know we're in homeroom. But bond order is literally just a special term for saying single, double, and triple. I would probably write that somewhere on a note card or somewhere really big. That's all it says. And so they might say, what's the bond order for this bond between carbon and nitrogen? And you would say, it's a bond order of 3 because now we're smarter and we don't say triple bonds. I don't know. That's literally all it is just coming up with saying bond order. So this is a single bond, double bond, triple bond. So your bond orders specifically tell you. Let's try one more question before you have to do your homework because I want to make sure that you're able to answer them. Consider the ball and stick models below. What they mean is circles with straight lines drawn versus space-filling orbitals are when you draw just the circles next to each other, okay? You have to be able to understand what they're asking you to represent. The carbon-carbon bond in which molecule has the lowest potential energy, and then part B, the carbon-carbon bond in which molecule has the lowest bond energy. Let's take a look at those, and then we'll be done. Okay, part A, the carbon-carbon bond in which molecule has the lowest potential energy. Grace.
I said 1
Because?
because there's 3 bonds.
Because there's 3 bonds, therefore shortest bond length. So I just want to be clear, if you wrote because there's 3 bonds, that's not the justification as to why it has the lowest potential energy. The justification is because it has the shortest bond length. So the distance between the adjacent nuclei are closest, which results in lowest potential energy. The carbon-carbon bond in which molecule has the lowest bond energy? Nelson?
2.
Because?
Because there's longer bond length.
Yep. And that's it. Notice that your justification has to be specific to what you're trying to justify it for. And you can't just use like the way that you solved it, but you have to use the actual chemical justification. All right, so if we take xenon and we look at the periodic table, xenon has 8, fluorine, each of them has 7. 7 times 4 is 28. So my total number of valence electrons is 36 valence electrons that need to be placed. Xenon goes in the center, and you probably went like this. I mean, you wouldn't know necessarily to put them in a certain way. You would attach your fluorines, that's what it says. Attach all terminal atoms with single bonds, right? Then it says to fill all of your terminal atoms octets. So that's 1, 2, 3, 4, 5, 6. And I just told Michaela that when I'm doing this for myself, I just go like that because I don't want to waste time hitting the paper with dots. All right, so now I'm going to add them all up, and I'm going to subtract from the total. So I have 6 dots around each of these. That's 24. 6 times 4 is 24. 26, 28, 30, 32. So minus the 32 electrons that are used, give me 4 electrons left over, and my rules tell me that I have to place them on the central atom. So now I go 1, 2, 3, 4. Keep your lone pairs together. You should always have 2 together. There is something called a radical that will have 1 electron alone, but we're not doing that. So your 2 lone electrons stay together, and then eventually tomorrow I'll teach you geometry. You'll start recognizing how to draw them a little bit more appropriately. But that's when you would check all your octets. So step 5 says check that everything has 8 valence electrons essentially, and if they don't, then you start making double bonds. Well, we don't need to make double bonds because all of my fluorines are satisfied, and in this case, I ended up with an expanded octet. So you would see you have an expanded octet. There are other atoms that will expand their octets. I'm going to write them down for you so that you kind of recognize them. It's definitely phosphorus. We just did that one. Xenon, we just did that one. Sulfur will expand, iodine will expand, and chlorine will expand. These are common ones to see as a expansion. Tassia, you good with that structure now? Okay. All right. This is so important. We are going to take note cards and write them down so that you don't forget this rule. This is called formal charge. So sometimes you will see I draw a structure, and maybe you drew a structure a different way. And you're like, well, how does she know that structure is supposed to be drawn that way? And before now, maybe it's just because I saw it and I knew that's the way it was supposed to be. But from now on, you will check what's called formal charge, and you will know for sure if the structure that you drew is likely to occur or not occur based on what you drew. All right, so it says in some cases, the atoms in a molecule can be assembled in different ways when drawing a Lewis diagram, which are electron dot diagrams. Formal charges are calculated to identify the most stable or likely structure, and the sum of the formal charges on each atom will be 0 for a neutral atom. Neutral atoms are 0, right? If we have a polyatomic ion, then the sum of the formal charges on each atom will be equal to the overall charge of the structure for a polyatomic. So if I'm doing sulfate, which we will do, That has a -2 charge. The sum of my charges should give me a -2. If it's not a polyatomic ion, then the sum of my charges should give me 0. And if you get anything else, then you did it incorrectly. If you got a -3 and you're supposed to have a -2, you did it incorrectly, which means your structure is wrong. So you need to redraw your structure. All right, so let's pass these out. Just pass them around the room. Do blue today. And there's a actual equation that I want you to write down to calculating formal charge. All right, so this one is just saying what's most likely to occur. I already expressed this to you. Should be equal to 0. If they're negative formal charges, they should always reside on the most electronegative element. So sometimes you will get a negative formal charge that may cancel with a positive formal charge to give you an overall charge of 0. The idea here is that it should always reside on the more electronegative element if there is a negative charge. So if a negative charge is present, it must be on the most electronegative element. So if I have an oxygen and a carbon, and I end up with a -1 on the carbon and a 0 on the oxygen, I did it incorrectly. The -1 should be on the oxygen because oxygen is more electronegative than carbon. Does that make sense? We'll practice these.
Are these all the cars?
Yeah. He didn't see that you had them. All right. So next, your calculation for formal charge is this. I wouldn't write this down exactly like this because this tends to look a little bit more confusing. The overall formal charge is equal to the number of valence electrons assigned to the neutral atom. That means when you look at the periodic table, the number of valence electrons that it's supposed to have is what that box means, minus the number of electrons assigned to the atom in the structure. So the atoms assigned in the structure come from, don't write anything down yet because I'm going to try to simplify it for you so that you remember, because this tends to be something that students forget as we move on. By the time May comes, you'll know you're supposed to do formal charge, but you'll forget how to do it. So the assigned electrons come from looking at a structure, and you add up the total number of valence electrons, the dots, essentially, and then you take your single bond and you make that 1. You're dividing the number of electrons in the bond by 2. So we know that a dash represents 2. Divide that by 2, that represents 1 electron assigned in the structure. So for example, this would be 2, 4, 6, 7. So it's the number of electrons assigned in the structure would mean how many does that atom actually contribute to the structure. We know that this is representing 2 because one of the electrons is shared from fluorine and one is shared from xenon. So assigned in the structure means how much is it contributing itself. All right, so we're going to do the number of valence electrons assigned to the number of electrons minus the number of electrons in the structure. So this to me sounds confusing because sometimes students accidentally reverse them. So I don't know how to help you except that we're going to call this goo. I think goo will stick in your head. Spelled G-U. You want to come up with something else? That's fine. But every year, students forget how to do this and they don't know which one goes first. So the word goo should help. So everybody say goo.
Goo.
3 times we'll say it. Goo, goo, goo. And now you remember formal charge means goo, hopefully. So in my mind, I think goo stands for got minus used, or given minus used. Goo, get it? Given is from the periodic table, used is what's in the structure. Goo. All right, so write that down on your note card. All right, so now we're going to look at actually drawing structures and figuring out which one's most likely to occur. So we have a structure called NCl3. So how do we know which one is more likely? We have a possible structure of NCl3 looking this way, or a possible structure of NCl3 looking this way. And you probably would put nitrogen in the center thinking it's least electronegative. If you look at the periodic table, sometimes it's confusing. Like, how do you know between O and Cl which one's most electronegative? And even nitrogen and chlorine, they kind of are headed towards the same corner, but they're close. In fact, if you look up the electronegativity values, they're both exactly 3.0. So if you were doing it based on least electronegative, you wouldn't have a choice, really. You'd have to figure out which one goes central by drawing them both and then calculating formal charge. So we're going to look at making this into a chart. And I am going to stress this tremendously. I'm forcing you to use a chart, or you can draw them directly on the atoms and demonstrate it. But you cannot write this in sentence format. Is that clear? Because they have asked this question as a free response on the AP exam, and I have seen responses where students are trying to verbally write sentences about it, but how do you identify this chlorine from this chlorine from this chlorine? So it gets way too confusing, and an AP reader is not going to have time for that, and they're just going to mark it wrong. So either you draw a table exactly like this, or you draw the charges on the structure, and I'll show you that example in a moment. So the first thing we're going to do, we're going to look at the valence electrons assigned. This is my GU, and this is my U, my G and my U, okay? So nitrogen, how many are given? How many do you have, got, you got? Yep, 5. So you fill 5 into that spot. How many are assigned? Let me pause on that. We'll do all of the givens first because I just put that up. So we have 5 given from nitrogen, and we know that chlorine is in group 7, so it has 7, right? So all of those chlorines have 7. That's my G, given. So now I'm going to subtract out my U's. So how many does nitrogen have in the structure that it's using? So you count 2, 4, 6, and then divide your bonding electrons by 2, which means 7. How many are in this chlorine? So everybody just look up here. I'll give you time to write them down. 2, 3, 4, 5. How many are in this chlorine? 7. 7. So we're going to fill them all in. Obviously, you should identify the chlorine that represents the central chlorine. It's the last one for me. So this is my central chlorine, and these are my 2 terminal chlorines. So now I subtract them. So I get a -2, 0, 0, and +2. I still end up with a sum of 0, don't I? And this is a neutral molecule, so it should give me a 0 charge. But this is not likely to occur because there's charge present. We want as little charge as possible. The only time that we want charge to be present is if it's a polyatomic ion. And if we have to have a charge at all, it's going to go on the most electronegative element. So this structure is not likely to occur. So let's evaluate the other structure. When nitrogen is central. So we're going to GU it. How many are given? Each chlorine has given 7. And nitrogen obviously is 5. You get those numbers from the group number on the periodic table. All right, the chlorine. Here we have 7, 7, 7. Nitrogen is, look, 1, 2. Half of your bonding makes 2, 3, 4, 5. So all of them end up giving you a formal charge of 0. So this structure is more likely to occur. Make sense? So every time that you draw a structure that you may or may not be confident on, you must do formal charge. And sometimes it will just require you to do that. It'll ask you for sure to demonstrate formal charge. So I am looking for a table. If I give you this question, I'm looking for a table. All right, which one is most likely to occur? So we have this structure, CSN. This one's tricky. I think I gave this to some of you when you had me last year. And there's lots of, it's possible that you could put this in either way. So now we're going to check formal charge. So sulfur and carbon both have electronegativity values of 2.5. So you have to pick which one is most likely. By default, which one do you think is most likely? Without even doing formal charge. Carbon in the middle, yeah, why?
Carbon's there in the middle.
Carbon always wants to have 4 bonds to it. It always does. To have carbon with lone electrons hanging around is very unlikely. So just as a general side note, second structure makes more sense, but we're going to calculate formal charge. So let's look at the first one, where carbon is not central. How many electrons do you have, or how many electrons are given? I'm trying to stick with the goo theme. Carbon has 4, sulfur? 6, thank you, Tasvia. Nitrogen? 5. So we fill them in, 4, 6, and 5. Now you check, I won't put them up for a moment. Go ahead and assign your electrons. How many are used in the structure? Now calculate your formal charge, subtract them, and then take a look up here. All right, what should my overall charge be? -1, because this is a polyatomic ion with a negative charge, right? So we want a -1 charge, and if we do have a -1, which atom should it be present on? Nitrogen, because nitrogen is the most electronegative out of the group, right? So what we end up with is a -2 charge, a +2 charge, which will cancel, and then we do have a -1 charge, and it's on nitrogen, which is what we said we wanted, but we have so much charge present that there's likely a better structure that exists. So let's check the other one. Go ahead and do that one quickly. When you're done, look up here. That one's most likely. So you end up with 0, 0, and a -1. You want a -1. It's on the most electronegative element. That structure is likely to occur. Simple enough? All right, you're going to do this one on your own. Draw the Lewis structure for sulfate and check it using formal charges. So step 1, we're going to do our structure drawing technique. So sulfate, just as a reminder, is a polyatomic ion, right? So when I'm drawing the structure and when I'm calculating formal charge, I better remember that there's 2 extra electrons assigned in the structure. So step 1, count the total number of valence electrons in the polyatomic ion. Go ahead. Did you get 32? Right, they're all in group 6. There's 5 atoms, 6 times 5 is 30, plus the extra 2 electrons that come from your polyatomic ion. So we end up with adding 2 to the overall valence electrons. So we get 32 electrons. All right, what's your next step? Always least electronegative in the center, which is obvious that this one should be sulfur in the center, and attach all your terminal atoms to it. So we attached our terminal atoms. All right, what's step 3? Fill all the octets of the terminal atoms. So dot, 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 dot. And then step 4. So first you have to check that everything right has their 8s, and then the extra ones go on the central atom, right? So we have 6 times 4 is 24, 26, 28, 30, 32. We're filled, right? So everything is satisfied here. We end up with 0. So there are no leftover electrons on the central atom, right? Okay. So now we need to check formal charge, because we think that this structure is complete, don't we? Okay. So go ahead now and check your formal charge. So in this example, I'm going to show you what I mean without making the chart. Watch. They're going to take all their formal charges and demonstrate them by pointing to the atom and showing the math right here without actually doing it. What you could do on the exam is do this, and then you should do an example formal charge calculation. Because I don't know that it's very clear that you just write -1, -1, -1, and -1 on this, that someone's going to understand what you mean. You have to show how you calculated formal charge. You can't just write numbers down. So if you wanted, you could say example formal charge and then show 6 electrons minus 7 electrons equals -1 charge. If you're going to do something like that. And you could even demonstrate this is what you are given valence electrons, and then these are used electrons in structure. You just need to be very clear on an exam that you know, or that you know that I know that you're talking about the right thing. So there's nobody just writing charges down on their structure, because I won't give you points for that. You have to demonstrate that you know where it came from. All right, what's the charge of sulfur in that one? 6 minus 4, so it's a positive 2 charge, right? So with that positive 2 charge, that cancels 2 of my negatives. My overall charge is minus 2. Does that seem likely? This thing is smothered with charges. We want zeros as much as possible. That's the most stable structure, is when your formal charge is giving you zeros, and then if there is a charge, it's just present on the most electronegative atoms. So I need to eliminate charge as much as possible, and the way that you eliminate charge is by making double bonds. So you don't really, there's no choice here. You have to make double bonds to oxygen. And remember, I told you that if double bonds are going to be made, you always make them to oxygen first, right? Well, this is obvious. You can only make them to oxygen because the only terminal atoms. But in the future, if there's other atoms, you always look for oxygen first. So I'm going to just start making double bonds. You make one double bond with an oxygen. As soon as you make that double bond, now your formal charge becomes 6 minus 1, 2, 3, 4. Eyes up here, eyes up here. 1, 2, 3, 4, 5, 6. So now that formal charge immediately went to 0. So you'll know that you need to make another one, because without me doing another double bond, my charge then was plus 2 minus 1. I would end up with a formal charge of negative 3 at that point, which would not be okay. So now I'm going to do it again, and I end up with 6 minus 6 equals 0. And then what's the charge on sulfur? It was 6, given. Used now is 1, 2, 3, 4, 5, 6 minus 6 equals 0. And the only charges are the negative ones on the oxygens, which gives me an overall charge of negative 2. So this structure is most likely to occur. Without formal charge, there's a good chance that you would have, just left it with the single bonds. Agreed? So you have to check formal charge every time that you draw a structure that you're not familiar with. Like, we can draw structures because we just have seen them so many times. We know what they're supposed to look like. But they will give you structures that you may not be familiar with, or they may just ask you to do formal charge. So number one choice is to draw a table to demonstrate formal charge. If you get to the AP exam at the end of the year and you forget that, then I guess you could do something like this to demonstrate it, but you should show an example formal charge calculation. Do not write formal charge in sentence form. It may ask you to justify, so you show your work like this, and then you can write a sentence that says, according to formal charge calculations, the overall charge results in a negative 2, the same as the polyatomic ion, on both the oxygens in the structure. And you demonstrated your formal charge already in a calculation. So you can summarize with one sentence, but do not write it all out in sentences. Good? Okay. Moving along. Bond energy. All right. Potential energy is going to be discussed at length in this course for many of the topics that we do. So you'll see me throughout the year with my arms out here, and then I'm going like this all the time, out here to here. And how many of you have been in physics already? One person's taken physics. You're in physics now. And then the rest of you are taking it second half?
Nope.
No physics at all for either of you? Oh, that was a mistake. Why aren't you taking physics?
I don't like it.
I don't like it either, but you're going to take it in college.
How do you know?
Yeah, I didn't take physics in high school, and it was a bad decision, because when I got to college, I was so lost. So you guys won't be as lost. Well, anyway, you probably have seen the picture of, like, I don't know, something like this, and there's a big rock, and there's, like, a guy, and he's ready to push this rock down the hill, and it goes down the hill. Yeah? So this is considered high potential energy, and this is considered low potential energy. So potential meaning, like, this rock has a lot of potential to go do something. You can think of it that way, right? So high potential energy means that it has a lot of energy that can fall and then get down here. Well, once it gets down here, it can't fall anymore, right? So it's lost its potential energy, potential energy is converted into kinetic energy as it's going down, right? So it does transfer energy because we can't lose energy. So something that is far away has high potential energy. Something that's very close, low potential energy. That's general. So if my hands are out here, I'm far away. So molecules, as they're formed, come from atoms, right? And atoms, here they are far away. They have high potential energy because they're ready to do something. They're looking for a mate. You can think of it like dating. High potential energy. Then we're getting closer and closer. And as they get closer and closer, they're losing their potential energy. It's going away. And as the bond forms, now we're so close to one another, we have very, very low to no potential energy. And all of the energy, because energy can't be lost, right? The energy gets released in the form of heat. So we have high potential energy going to low potential energy. Where does the energy go? But out as heat. So when bonds are formed, it releases heat. When bonds are broken, it absorbs heat. I've said this to you in the past week also. But now you're getting an idea of where does that energy come from. It comes from the potential energy. So things that are far away, put your arms out because you will need to know this throughout the year. High potential energy, say that. Okay, now bring them closer. Losing potential energy, yeah? And now low potential energy. Where does that energy go? Out as heat. Get it? Okay. So that's what this is showing you, is that you have these high forces of attraction. They're really desiring to get together. So high potential energy, then they get closer. All right, watch what else happens. And I'm going to show you this all in the slides, and we'll touch on it again. Molecules vibrate, right? So, trying to find if I have something. Let's do it like this.
You should teach physics too.
Yeah?
Yeah, like next sem.
I don't know physics.
I think a really big thing. Like next sem, third block.
That seems awful. It almost seems as awful as teaching bio. That would be death. I might actually quit my job if I ever had to teach bio.
I think it's a little bit.
I would just have you guys make note cards and memorize the whole block. All right, so we have our molecules, high potential energy coming together. All right, watch what happens. Molecules don't just stick like this, right? They vibrate. So as they're vibrating, they cross paths. So what is the center of each of these atoms? The nucleus. So we're really talking about the nucleus, or the nuclei of these coming together. And as they come together, they're at absolute low potential energy right here, the lowest it can go. But the second it starts vibrating past the other cup, the nuclei now have, do you see that? Distance again. It's not distance this way, but it's like passing distance going this way. So once you gain that distance again, you start increasing your potential energy, don't you? So you're going to see some graphs in a moment that try to mess with your head. You just have to realize that as the molecules pass each other, they're gaining potential energy again. When they're head-on, lowest potential energy. Yep.
So is it like if your hands went like this and then they cross like that?
Like a spring. Yeah, just like a spring. And that's what bonds are like. They're like springs. They're bungee. And if you heat them up, they bungee faster. If you slow them down, then the molecules are really slow, right? Okay. So, bond energy. Energy is released during the formation of the bond. This is so important. I think we should make another note card. That's how important it is. Yeah. Because when we get to thermodynamics, this is fundamental. You must understand heat release, heat absorption, all of that. So energy is released during the formation of a bond. Potential energy decreases as the atoms move very close together. The same amount of energy must be added in order to break that specific bond. Potential energy increases as the atoms move away from each other. So very important is that we talk potential energy. So bonds formed release energy. This is called exothermic. And all of your values will be negative. We'll use this throughout the year. So bonds formed release energy. It's exothermic and they have negative values. Bonds broken absorb energy. That's endothermic. And they have positive values. These are equal to each other, but opposite. You don't have to write it in the same spot that I did. They're equal but opposite. All right, so the amount of energy released has to be equal to the amount of energy absorbed for the exact same bond, right? So this is going to release energy, and you may want to jot down on your note card, how is it releasing energy? It's because potential energy is going away, right? Energy has to be transferred, so potential energy decreases, it gets released. The next slide is exactly what you just wrote down. It says the amount of energy that is required to break the bond between two specific atoms in a molecule is equal to the amount of energy that's released when a bond forms between the same two atoms, but an opposite sign. So look at this example. I think it's sodium chloride. Oh, hydrochloric acid. So hydrochloric acid, as this bond, if I'm breaking this bond between H and Cl, here it is, broken. Delta H is the enthalpy, which we'll get to, which right now all you need to know is that that means heat or energy. I'll jot this down. This is called enthalpy, and this is the heat, and this is the temperature at which they're breaking the bond. So they're breaking this bond at 298 degrees Celsius. So that's what this says. Or actually, this is in Kelvin. Let me check. I don't remember for some reason. Does it say it right there? I gotta think of my units for a moment. I guess it could be degrees Celsius. Could be Kelvin, though. It depends on the units when we calculate for enthalpy. So I don't know. I'll have to decide later. No. I'm going to say, I don't know. Probably Kelvin. If I think about it more clearly, probably Kelvin. All right, so this is the amount of energy to break the bond between H and Cl. It takes 432 kilojoules per mole. If I'm forming that bond, it's going to be the exact same amount of energy, but negative because it's releasing it. Same exact thing. All right, here's that diagram that I said. So probably every single exam for the last 3 years that I've seen the new curriculum has given this as a multiple choice question. And so they show you this graph, and then they usually say, without pointing out for you the HH bond length, they just give you a graph and they say, which of the following points has the lowest potential energy in this system? So they'll label it like point A, B, C, D, and then you choose the correct multiple choice. All right, so everybody just take a look at that and answer that question. Which of the following points has the lowest potential energy? So really simple if you look at what? Like the axes, right? The axes tell you energy, and it shows it to you there. And then the internuclear distance is increasing as you go this way. So the lowest distance is this one, has the least amount of distance. So your mind might think, all right, it's the closest, so it must be the lowest potential energy. Because remember I said as you're far away and getting closer, you have low potential energy. But what is this a picture of? They're overlapping. So as they overlap, their potential energy is increasing because their distance is getting further away. They can ask you any variety of questions about this graph. Some of them do say, what is this point? And then there's a bunch of multiple choice answers where you have to describe what's happening at this point. And then just recognizing that this is the lowest energy system because they're basically head-on. And then this is as they are coming together. So it says as the atomic radii of bonding atoms increase, the bond length increases and the bond energy decreases. It's a lot of words to get together. A closer proximity to the shared electrons allows for a stronger force of attraction between the protons and the bonding electrons. All right, so I have my two atoms and their protons, and as they get closer together, the electrons that are around here, I feel like this is probably best to do this. And then we have electrons. This is terrible drawings, but I think you'll get it. All right, so as they get closer together, these electrons can be attracted to this proton, and these electrons can be attracted to this proton as they get closer together, which means electrostatic forces of attraction are increasing, right? Force of attraction between protons and bonding electrons is increasing as they get closer together. When the force of attraction is greater, it requires more energy to break that bond. So karate chopping this in half, the stronger the bond, the more bond energy is needed to break the bond. So that's what this is saying. So if bond length increases, so the longer the bond, the weaker the energy is, or the less energy is needed to break that bond. Get bond energy and bond length? So long bonds are easy to break. Short bonds are harder to break. It's karate chopping a long piece of wood and a really, really small piece of wood, right? If you ever watched Karate Kid, or you've ever done it yourself, a really long piece of wood is easier to chop than the short piece. Yes?
So when it overlaps, what happens then?
Well, the overlapping is just them passing. You mean when they passing each other?
Yeah, like how does
The bond?
yeah.
The bond length at that point, I guess, would be longer. You would consider it longer, and then it would be easier to break. That's not really talking about this, though.
Okay.
It's just like, in general, the bond, which we'll get to in terms of single bonds, double bonds, and triple bonds. That's what this is really talking about. So bond strength increases, then bond energy is greater. So we have different types of bonds, and the bond length comes from the size of the atom. So again, periodic trends never go away. You have to know, who's the biggest atom? Francium. So if I look at, all of these are single bonds. So carbon is our common atom here. Look at chlorine, look at bromine, look at iodine. Who's the biggest? Iodine. So its nuclei is much further away, its nucleus is further away than of the other electrons, right? So if we draw a visual representation of this, I have carbon, and then, what is that, chlorine? So that's carbon and chlorine. Then I have carbon, and then the next one, and carbon, and then the next one. And these are their nucleus. So it's clear that in this one, my bond length is much larger because I'm going from here to here. Remember, bond length is the distance between adjacent nuclei. So here's a nucleus, here's a nucleus. The distance between adjacent nuclei gives me my bond length. This is the longest bond. So the energy required to break that bond is less than the energy required to break the one that's closer. Make sense? So you just have to relate that. Bond energy and bond length are related. So as atomic radii increases, bond length increases, potential energy increases, and bond energy decreases. You will get asked all of those. So you'll get asked what happens to the energy, potential energy, what happens to the bond energy, what happens to the bond length. Which one of these has the lowest potential energy? CCl, right? Because they're closest together. All right, consider these space-filling models. Space-filling models are literally just circles that are colored in. They're like dense little balls. They're showing you two different atoms. So part A, which molecule has the least amount of potential energy associated with its bond? And then part B, which bond has the lowest bond energy? So I'm going to give you guys a minute to look at this.